This video is just going to provide a bunch of practice problems for reactions involving alkyl halides through the Sn1, Sn2, E1, and E2 pathways. They're going to be pretty high-level problems, some of them at least in the format that you might see on an exam. So if you have an exam that's covering this stuff in the near future, don't worry, just watch this, do the practice problems. Now let's try this one. Pause it, give it a go, and I'll get back to you. Okay, so for this problem, um, the right answer is actually that there is no answer. And if you're wondering why, I understand. I would expect you to expect um, something like this, because this base here is tert butoxide, which is a super bulky base, in fact, which is too bulky to act as a nucleophile. So you won't see any Sn2 from this. So it would make sense for you to expect an E2 mechanism. But let's think about what we mean when we say an E2 mechanism. We need beta hydrogens for our base to remove in order to flip these electrons to form that double bond. And we'll end up with a product like this. So now let's turn our attention to the original problem. We need beta hydrogens that are available to use for this elimination. If we look over here, there are no beta hydrogens on this carbon because it's connected to 4 different carbons. So it has its full octet just in carbons alone, meaning that there are no beta hydrogens on that carbon, so we can't use any of those. But I can hear you saying, wait, there's a beta hydrogen on this beta carbon. But I would encourage you to think about stereochemistry. For an elimination to occur, the beta hydrogen must be taken from an angle completely opposite to the halide or the halogen that it's eliminating. That's why you get more of like a flap or trap door type of action where everything happens in a line. The hydrogen has to be opposite in terms of stereochemistry to the halogen. So if we return here, this carbon is coming out towards us, right? And both of the other carbons are in plane, meaning that that beta hydrogen has to have this stereochemistry. Now what's the problem? This hydrogen and this iodine are on the same plane in terms of stereochemistry. So it can't be used to eliminate it, because there is no point in time in which the hydrogen will be 180 degrees opposite to the iodine. That's why there is no reaction when you run this. Okay, so this one uh, involves 2 reactions that look very similar, but it's a 3-part problem. First, what is the common pathway? Second, what is the final product of each? And third, or 3A and 3B, which reaction is faster and why? Give it a go. Okay, so as I deliver the answer, the first problem only has 1 answer, but the second one has 2. This is why. This is the only answer for the first one, and these are the 2 solutions for the second one. The natural response when you see uh, this type of differentiation between solutions is there's probably a different reaction pathway. But remember when I said that there's a common pathway? The only reason why the first one has one solution and the second one has two is because this is achiral and these are chiral. That is because this carbon here is the only potential asymmetric center, and it has two groups that are exactly the same. But this carbon, which is the same as this carbon over here, has one phenyl group as well as one just straight cyclohexane, meaning that like those along with this bromine and a hydrogen back here uh, have four different groups on it, so it can be chiral. Oh, so it is chiral. So we need to establish that these two different possibilities can both happen. And that's under the assumption that you can even get two different answers. Remember when we did uh, E2 and SN2, uh, stereochemistry was very important. It was very important to pay close attention to the stereochemistry because that would dictate the solution. Why can we get two enantiomers as our solutions here? It's because the common reaction pathway, which was part of the question, is Sn1, meaning that this reactant went through solvolysis. Essentially, over time, in the right solvent, uh, the leaving group acted as such, formed a carbocation. Now, the reason it can do this, as I said, it needs to be in the right solution, is because the cation is stable, stable enough for this to be favorable. The reason why this happens is because uh, these uh, phenyl groups provide an insane amount of resonance. Let's take a look. Now, the electrons from this double bond can move this way to create this resonance structure, which then can do the same thing this way to have resonance with this, which then can keep going. We can keep it going. Go over there. And that has even more resonance with this. And we can push these electrons back down to come back to the original structure, but the cation returned to the original place. And if you haven't noticed, there's another ring. So we have twice as much resonance even on the other side. And that could answer the final question, which is which reaction happens faster. And that is the first one, because this cation is more stable than this one because it has twice the resonance, as this one doesn't have any double bonds over here. Here's another one where we're comparing two similar reactions and identifying what the product is, but also which reaction is faster. Give it a shot. Yeah, both of these run an SN2 reaction, where the final product is this. Now, which reaction happens faster? We can zero in on the starting materials and notice that the only thing that differs is the leaving group, chlorine and bromine, the halogen. So really what we're focusing on, because the only thing that's different is really the final product, but only within the leaving group, because all of this stays the same. Um you still get just this for both of them, right? But you have on this side you have an additional chlorine with a negative charge, and on this side you get an additional bromine with a negative charge. So really all we're doing is seeing between chlorine and bromine which is more stable with a negative charge because that one will fight less to stay where it was to begin with. The one that's more stable with a negative charge will be more inclined to dissociate. In other words, it's a better leaving group, therefore the reaction will happen faster. So the way you can tell this is if you're looking at the periodic table, on the right side you have the halogens. Bromine is below chlorine. Pretty much that means that it's bigger, therefore it can disperse the negative charge more. Just like how with the previous example with resonance, the point of resonance is that you're spreading that negative charge around. Whereas chlorine, that negative charge is just in a tiny place, which makes it unstable. Whereas for bromine, that negative charge is split up in a bigger area, so it's more comfortable having that negative charge. Therefore, the reaction with bromine happens faster. Here's another comparison one. Tell me which reaction happens faster. Okay, so the first one doesn't react. And the reasoning for that is because, remember this tert butoxide, way too bulky to run an Sn2 uh, when there's any beta branching, which this one has. Uh, so most of the time, this is going to be an E2. However, big however, where is the beta hydrogen? There isn't one. So the tert butoxide can't remove a hydrogen here to kick off the carbon, the chlorine, because it's bonded to four carbons. There's no hydrogen. So that can't react. Okay, so if the E2 reaction just doesn't happen at all, the Sn2 with the nucleophile just has to be faster. But the truth is, this doesn't react either. And the reasoning why is because um, there's just too much going on over here. There's just too much beta branching. The the nucleophile can't get in because there's too much stuff going on. So whenever you see a neopentyl system like this, understand that your professor might be pulling a trick on you because it just doesn't react. But also, like more importantly, understand why. And that's because the lack of beta hydrogens for an E2 and the lack of space for a nucleophile to come in through to perform an Sn2. Try this. What reagents or solvent do you run this through to end up with these products? These products in an equal ratio too. And more importantly, probably the harder part of the question will be why? Why do you get 50-50? Okay, so you have a 50-50 a 50-50 ratio between the retained stereochemistry, which is this one, and the inversion of stereochemistry. You end up with things that are 50-50 when you see randomness, which, as we know, happens through carbocations. So what needs to happen to make this turn into a carbocation? That's right, isovolysis. We need this just to break straight off. And to do that, we can't have a strong nucleophile or a strong base as our solvent. So the right answer here is just methanol. That's it. Now the hard part, or not the hard part, the important part of this question is why does this work so well? And that's because it's only going to be a secondary carbocation. It's not going to be that stable. It won't be that fast. But this resonance stabilizes that cation. Like this resonance makes this ion very stable. So that's it. Okay, now we have the same problem, but we changed the reagent. Matter of fact, this one almost never happens to the point where this is pretty much the only solution. But this problem, I'm asking you to draw a mechanism. Like, why does this happen? So pretty much, you just have an Sn2 mechanism where the methoxide uh, removes the bromine leaving group, and you have inversion of the stereochemistry, and that's it. Okay, let's try this one. Things you need to know before you get started, in case you didn't know. Deuterium is just an isotope of hydrogen. Uh, it's just hydrogen with an extra neutron, so it's slightly heavier. But it reacts exactly the same as hydrogen does. The only reason we use it is to mark reactions so we can gauge their mechanisms. So you'll be able to tell which carbon ends up where. Uh, Also, OTS is a tosylate, which is a fantastic leaving group that we use industrially. And then other than that, uh, just try to find out what the solution is or what the final product is, but there's two of them. What are the two products of this, and why does it end up that way? Okay, so with this and with anything else that might be difficult, again, the best way to go about this is to try drawing a reaction mechanism. Maybe the first thing you can notice is the solvent, methanol, being a polar protic one. And as we know, polar protic solvents tend to favor uh, Sn1 and E1 reaction mechanisms. They tend to speed up the rate of solvolysis. However, like what would solvolysis entail in this case? Because this carbon is a primary um, alpha carbon, meaning that the cation of this is a primary carbocation, which is insanely unstable. We almost never see that happen. So solvolysis for this is nearly impossible. So we should move on to other possibilities. Okay, so solvolysis can't happen because the cation would be too unstable. And we aren't in basic conditions because the solvent is not a strong base in any way, nor is it a very good nucleophile. But because it's not basic conditions, we're not really going to see any E2. But are there any good nucleophiles that can act as a nucleophile? We already know OTS is a very, very good leaving group, but we also have this sulfur, which is, if you look on the periodic table, um, right under oxygen, has two lone pairs, and even more so than oxygen, can act as fantastic nucleophile. So we see Sn2. Okay, so now we have a sulfur that is bonded to two adjacent carbons that are bonded to each other with nothing in between, giving us pretty much a triangle, a sulfoxide, an epoxide with a sulfur instead of an oxygen. It's extremely unstable. So this solvent that couldn't react before can now run an Sn2 type, act as a nucleophile, run an Sn2 back onto the carbons to stabilize that molecule. But this can go either way. This can go here, or it can go here, which is why, and following that, the carbon's can fill in this way. Okay, let me redraw this over here. Um, just to illustrate, this can go either way. Like let's see what happens when it goes both pathways. If it goes to the side that the deuteriums are not on, we end up, well, also pushes this off. Then we end up with this, which needs to be deprotonated again by more methanol to give us this answer, which is different than if the methanol were to bond on the same side as the deuterium, which would give us this, which when deprotonated turns into this, which is why we have two different solutions depending on which carbon uh, is utilized for the Sn2 reaction. Okay, write the product or products and give me a mechanism. Pause and I will do it after. Okay, this is the major product and this is the mechanism for how. Okay, we have a polar protic solvent, we have nothing basic, we have a tertiary alpha carbon. Um, Everything's pointing towards solulysis, so the leaving group leaves, which leaves us with a carbocation. Um, if you saw this five-membered ring and the solution six-membered ring, you could probably put together that this ended up as a ring expansion. Because anytime you see a four or five or even three-membered ring with the opportunity to expand, it will because it wants to be more stable. So that gives us this, and the next logical step would be for the solvent to bond to this cation, but we're not done yet. This is still not the most stable carbocation. We have a rearrangement. So this is the carbocation that the solvent reacts with. It just ends up needing to be deprotonated by another molecule of ethanol. And that gives you your final solution. Yep, good job.